Thanks, Eugene. It's been 6 years since I last gave my EMNLP talk, and so it's good to be able to talk to you again today. In recent years, people have started to explore new opinion mining tasks, and one such task is debate stance classification. So given the debate post written for a two-sided debate topic, the goal of debate stance classification is to determine the author's stance which can be for or against. And so let's take a look at this example debate topic. Should abortion be allowed? If we are given this debate post, women should have the ability to choose what they do with their bodies. A stance classifier should assign the for stance to it. On the other hand, if we are given this debate post, technically abortion is murder, blah, 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 a stance classifier should assign the against stance to it. But oftentimes, it's important to determine not only the author's stance, but also the reasons why she supports or opposes the issue under debate. And so this task of post-level reason classification might be of interest to NLP researchers. Given a set of reasons associated with each stance in an online debate, identify those reasons that an author used to back up her stance in the debate post. And here's a more challenging version of the task that we call sentence-level reason classification. In this case, I want to identify not only the reasons an author used in her post, but also the sentences in the post that she used to describe each of her reasons. And so let's take a look at this example post. I feel that abortion should remain legal, or rather, parents should have the power to make the decision themselves. Let us take a look from the social perspective. If parents cannot afford to provide for the child, it's understandable that abortion can remain as one of the options. And so here's a post on pro-abortion. And in this case, the author used in her post two reasons to support her stance on pro-abortion, namely, is a woman's right to abort and unwanted babies are a threat to their parents' future. And these two reasons are described in the first sentence and the third sentence of the post, respectively. So our goal in this work is to examine post and sentence level reason classification in ideological debates. Reason classification in ideological debates is potentially more challenging than that in other debate settings like congressional debates because in part of the use of sarcasm and insults. And our specific goal here is to examine how automatically computed stance information can be profitably exploited for reason classification. And even though there's a close interplay between stance classification and reason classification, there's no guarantee that using automatically computed stance information can benefit reason classification because if the stance is incorrectly determined, then the reasons may also be incorrectly determined. And so we hypothesize that the effectiveness of automatically computed stance information would depend in part on the way it is exploited in reason classification systems. And as a result, we will examine a set of stance-supported reason classification models that differ in terms of modeling sophistication. Okay? So here's the plan for the rest of the talk. We'll describe our corpus and our annotation procedure, and then we'll describe our baseline reason classification system, and then our stance-supported reason classification systems. And finally, we'll show some evaluation results. So let's start with corpus and annotation. We employ 4 data sets taken from createdebate.com. These data sets contain debate posts collected from 4 different debate topics. Do you support abortion, gay rights, Obama, and should marijuana be legalized? Here I have the size of the data sets as well as the percentage of posts labeled as 4. The last column of this table shows the average sequence length. If you remember, a post can form post sequences, meaning that each post in the sequence is a reply to the immediately preceding post in the sequence. And this last column shows the average number of posts in the post sequence. So for instance, for abortion and gay rights, the average number of posts in the post sequence is approximately 4. Even though these stance labels are provided by the authors, the posts are not annotated with reasons, and Therefore, we need to annotate the reasons ourselves. And in our reason annotation procedure, there are 5 steps. For each debate topic, we have 2 human annotators who first independently examined each post and identified the reasons the authors used to support their stances. And then they discussed and agreed on the reasons classes identified. And after that, they independently annotated each post with these reason classes. Specifically, they labeled each sentence with the set of reasons the author expressed in that sentence. And any sentence that does not belong to any reason class was assigned the none class. And after that, they are asked to collapse the rare reason classes, specifically those classes that occur in less than 2% of the sentences, into the other class. And the reason for collapsing rare reason classes is that these rare classes are typically less important, and trying to model these rare classes would increase modeling complexity without much benefits for our purposes. And finally, for each multi-label sentence, we ask the annotators to pick and retain only the reason that was highlighted the most in it. And again, multi-label sentences comprise only less than 3% of the sentences in our data set. And for the purpose of avoiding modeling complexity, we ask them to just select one of the reasons in these multi-label sentences as the reason for these sentences. Here are the reason annotation statistics. We managed to annotate most, but not all of the posts in our data set. And around 20 to 43% of the sentences do not contain any reason in this data set. And here I also have the inter-annotator agreement scores expressed in terms of kappa with respect to sentences and post. And here you can see that we have substantial post-level agreement and high sentence-level agreement. The major source of disagreement is this. Annotators, while agreeing on the reason class, differ on how long the text span for a reason should be. And you can see that this hurts sentence level, but not post-level agreement. And so that explains why the sentence level agreement scores are lower than the post-level agreement scores. Okay. So now let's take a look at our baseline reason classification system. Our baseline classification system is the sentence level reason classifier that determines whether a reason is expressed in the sentence or not. If so, it assigns the sentence its reason class. Okay. Otherwise, we assign the label none. We create training instances, one for each sentence in each training post. The class label is human annotated reason label, or none if it does not contain a reason. And as our learning algorithm, we employ maximum entropy. Our baseline system uses 5 types of features, including unigrams and bigrams, dependency-based features that use the 2 arguments involved in a dependency relation. We optionally generalize one or both of these arguments with its part-of-speech tags and their polarity labels. We have 2 quotation features. The first one encodes whether the sentence is a quote, because a quoted sentence typically does not represent the author's opinion. We have another feature that encodes whether the sentence follows a quote, because typically such a sentence would express a counter-argument. And we also have some positional features that encode where a sentence appears in the post. And finally, we have some frame semantic features that encode the semantic representation of the sentence concepts using FrameNet features, but we are not going to go into the details here. Okay. Again, if you remember, our baseline system is a sentence-level reason classifier. So the question is, how can we produce post-level reason labels for a post? Because we are not only interested in measuring the performance of reason classification at the sentence level, but we are also interested in measuring the reason classification performance at the post level. And here we adopt a very simple solution. We take the union of the set of reason labels assigned by the classifier to each of its sentences and use those as our post-level reason labels. In other words, the post-reason labels are derived automatically from the sentence-level reason labels. Okay. Now let's take a look at our stance-supported reason classification systems. In particular, we have 7 systems that differ with respect to the levels of modeling sophistication. Now let's start with pipeline systems. So in pipeline systems, we use a stance classifier to identify the stance of a post, which can be for or against. After identifying the stance, if the post is classified as for, we then use the for stance reason classifier to label each of its sentences with the reasons. And if the post is labeled as against by the stance classifier, then we use the against stance reason classifier to label each of its sentences. And so these stance-dependent reason classifiers are trained in the same way as the baseline stance-independent reason classifier, except that the for stance classifier is trained only on the for posts, and the against stance classifier is trained only on the against posts. Okay? And in essence, each stance-dependent reason classifier estimates this probability, P of R given ST, where R is a reason label, S is a stance label, and T is the sentence under consideration. Okay? So now the question is, how can we train the stance classifier? We employ two different methods. The first method trains a binary classifier that assigns a stance label, which can be for or against, to each debate post P independently of the other posts. So in this case, each training instance corresponds to the debate post. The features that we use here are the same as those features that we used for reason classification. And as our learning algorithm, we use maximum entropy, which estimates the probability of a stance label given the post, because again, we are doing stance classification here. Okay? Our second method for stance classification is the same as the first method, except that we recast stance classification as a sequence labeling problem. Again, in these sequence labels, they take as input a post sequence PS, which is composed of the end post in the sequence, and they output a stance sequence S with one stance for each of the posts in the sequence. And the sequence model estimates this probability P of S, which is the stance sequence, given PS, which is the post sequence, and returns the most probable stance sequence. And the motivation behind using a sequence labeling approach to stance classification is this. Since a post in the post sequence is replied to its parent post, its label should be determined in dependent relation to its parent posts. And to train these sequence models, we employ MEMM. So we have two pipeline systems that adopts this pipeline system architecture, but differ with respect to the stance classification model. In particular, P1 classifies the stance of each post independently, and P2 uses sequence learning for stance classification. But otherwise, these two pipeline systems are the same. Our next stance-supported reason classification system uses joint inference. And the motivation behind using joint inference is that in the pipeline systems, errors can propagate from the stance classification system to the reason classification system. In particular, if we have an incorrectly labeled stance, then that would lead to incorrectly labeled reasons. And so as a result, we use integer linear programming to perform joint inference over the outputs of the independently trained stance classifier and reason classifier. For the stance classifier, we use the sequence labeling model in pipeline system P2. And as our reason classifier, we use the stance-independent baseline reason classification system. And the question is, what IOP constraints do we have here? And here are the IOP constraints we use. If a post contains a for reason, its stance label should be for. A post stance labeled as for should contain a for reason. And similar constraints are being defined for the against label. Okay? Now let's move on to our next stance-supported system, which uses joint maximization. So joint maximization is another way to address the error propagation problem inherent in the pipeline system. So again, if you remember, this is the architecture for the pipeline systems, where the stance classifier estimates the probability of seeing a stance S given post P, and these stance-dependent reason classifiers estimates the probability of a reason label given the stance S and the sentence T under consideration. And our goal in joint maximization is to determine the stance label using not only the stance classifier, but also the stance-dependent reason classifiers later on in the pipeline. In other words, we let the reason classifiers influence the choice of the stance. So the question is, how can that possibly be done? To do so, we find the stance S that maximizes this particular probability. If you remember, This is a probability that is provided by the stance classifier that is used in pipeline system P1. And this probability is provided by the stance-dependent reason classifier. And this product is overall the sentences in the post under consideration. And we call this joint maximization system J1. Now let's move on to joint maximization system J2, which is the same as J1, except that we recast stance classification as a sequence labeling task. So in this case, given the post sequence PS consisting of n posts, this model J2 finds the stance sequence S and reasons R that jointly maximize the probability of seeing the reason sequence and the stance sequence given the post sequence. In this case, Ri is the list of reasons assigned to the sentences in the ith post in the post sequence. And the reason sequence R and the stance sequence S that jointly maximize this probability can be found efficiently using dynamic programming. It's just a modified version of Viterbi. Okay. Now, let's move on to our last joint maximization model, J3, which is motivated by the following observation. If you recall, post in the post sequence is a reply to its preceding post. And we found that in our data, in many cases, a reply is a rebuttal to the preceding post where the author argues against the points raised in the preceding post and then provides her reasons for the opposing stance. And because of this observation, we hypothesized that the reasons mentioned in the preceding post could be useful for predicting the reasons in the current post. And so in our joint maximization model J3, which is built on top of J2, we augment the feature set of the stance-dependent reason classifiers with the set of reason features, with one binary feature for each reason class, indicating the presence or absence of that reason predicted for the preceding post. Okay? So before we move on, let's recap the 7 stance-supported systems that we talked about so far. We have 2 pipeline systems that differ with respect to whether sequence labeling is used for stance classification. We have one joint inference system that uses ILP. And finally, we have 3 joint maximization systems. J1 is the joint version of P1, J2 is the joint version of P2, and J3 is the same as J2, except that the features for training the reason classifiers are augmented with the reason labels predicted for the preceding post in the sequence. So now let's move on to evaluation, where our goal is to evaluate the stance-supported reason classification systems. In particular, our evaluation is centered around this particular question. Will reason classification performance improve as we employ more sophisticated methods for modeling stances and reasons? And not only are we interested in the performance of reason classification, we are also interested in the performance of stance classification. In particular, we want to know whether stance classification performance can be improved when stance classification is jointly modeled with reason classification. And in our evaluation, we use 5-fold cross-validation for each debate topic. To measure the performance of stance classification, we use accuracy. And to measure the performance of reason classification, we use F-score, micro-average over all the reason classes except none class. And we have F-scores for both sentence-level reason classification and post-level reason classification. And if you remember, our post-level reason labels are derived from the sentence-level reason labels. Okay? So here are the results of reason classification expressed in terms of F-scores on our 4 data sets. Again, we have sentence-level scores as well as post-level scores for our baseline system. And here, it should not be surprising that sentence-level scores are lower than the post-level scores. Here are the results of our 2 pipeline systems. As you can see, both pipeline systems significantly outperform the baseline system, which suggests that reason classification can be improved even when stance information is incorporated into a reason classification in a fairly simple manner. And also, P2 outperforms P1, suggesting that better stance classification in terms of sequence modeling can indeed lead to better reason classification performance. Now let's take a look at the results of the ILP system. As you can see, ILP beats pipeline system P2 on 2 datasets and achieved the same level of performance as P2 on the remaining 2 datasets. And this suggests that joint inference is no worse and sometimes even better than pipeline learning when exploiting stance information for reason classification. Now let's take a look at two of our joint maximization systems, J1 and J2. You can see here that J2 outperforms J1. Again, that means that better stance classification performance via sequence modeling indeed leads to better reason classification performance. Also, both J1 and J2 outperform their pipeline counterparts P1 and P2, suggesting that joint learning is indeed a better way to incorporate stance information for reason classification than pipeline learning. And finally, here are the results of J3, which again exploits reason labels predicted for the preceding post in the post sequence. And we can see that J3 significantly beats J2 for 2 data sets and yields small, insignificant gains for the remaining 2 data sets. And so these results suggest that the reasons predicted for the preceding post provide useful information for reason classification. And also, J3 significantly beats the baseline by an average of 6.7 and 7.5 points at the sentence and post levels, respectively. And overall, these results suggest that the usefulness of automatically computed stance information depends in part on the way it is exploited. And let me conclude by showing you some stance classification performance results. And here are the results. And you can see that J3 achieved the best stance classification accuracies for all data sets. J3 is better, sometimes significantly so, than the best pipeline model P2 on all the data sets. And this suggests that joint modeling of stance classification and reason classification has a positive impact on stance classification. So let me conclude here because otherwise Yejin will not be happy with me. Thank you very much.
We have a few minutes for questions. Well.
Hello. Very good talk. Very clear what your point. One thing that I guess I missed. So you described these 3 joint models, and it seems to be on the second and the third one. Is that right? You use dynamic programming.
That's correct.
And what did you do in the first one? I wasn't sure.
Okay, so the first one, it tries to maximize this particular probability. So okay, so this is the probability that it tries to maximize. It tries to find the stance that maximizes, this probability. So again, there's one portion of this, probability that came from the stance classifier. Another portion came from the reason classifier. And so you want to choose the stance that makes this entire thing happy.
Right, and was that also dynamic programming? Or?
No, because there's no sequences involved in this. And so we just need to determine this for each post independently of other posts.
Okay.
Hi, thanks a lot for the talk. I'm wondering whether your reasons are somehow topic specific. So I guess that you can have reasons for Obama and all this kind, I don't know. Obama is very good for our external politics, and probably abortion has nothing to do with external politics whatsoever. And then if so, how does it scale in terms of domain adaptation and topic adaptation? So can you use this approach to classify debates on something completely different?
At least my current answer is no. And I guess that's somewhat unfortunate. But of course, as far as annotation is concerned, I don't have a way to make it scalable at this point. But of course, if you're trying to develop systems that can, identify reasons automatically, maybe we can adopt a clustering approach. And in that case, I think that, the approach itself would not be domain dependent. Because, if, we are training this systems like this on annotations, definitely, since the annotations or the reason classes are domain specific, the system will have to be domain specific as well. But if we adopt a clustering approach, then there is a hope of being able to develop systems that are domain independent. But as far as annotation is concerned, I haven't thought of a good way of being able to maybe do some sort of domain adaptation to adapt annotations we had for one domain to another.
Okay, so we'll have to move to the second talk. Let's first thank our speaker.
Thank you very much.
And it so happens the second talk will be also given by Vincent. The title is Chinese Zero Pronoun Resolution, an Unsupervised Probabilistic Model Rivaling Supervised Resolvers, work done by Chen Chen and Vincent, and Vincent is going to give the talk again.
Apparently, not too many people are interested in Chinese. So maybe you know that zero pronouns occur in many languages, such as Spanish, Italian, Korean, Chinese, and Japanese. And I believe that most of you actually know what zero pronouns are, but in case you don't, here's an informal definition. A zero pronoun is a gap in a sentence that is found when a phonetically null form is used to refer to an entity. And building on this definition, we can define an anaphoric zero pronoun as a zero pronoun that is anaphoric. In other words, an AZP is a zero pronoun that co-refers with one or more preceding noun phrases in the associated text. So here's an example in Chinese that is being translated into English. Russia is a consistent supporter of Milosevic. Pro has proposed to mediate the political crisis. So in this case, pro is represents zero pronoun, and you can see that in this case, this English sentence is of course not grammatical because in English we don't have zero pronouns. But just by looking at this English translation, you can see that this pro here is anaphoric. It refers to Russia. Okay, so it's an anaphoric zero pronoun. So from this example, hopefully you can see that zero pronoun resolution is more challenging than overt pronoun resolution because zero pronouns lack the grammatical attributes useful for overt pronoun resolution, such as gender and number. And zero pronoun resolution is typically composed of two steps. AZP identification, which involves extracting from a text all the zero pronouns that are anaphoric. And the second step is AZP resolution, which aims to identify an antecedent of an anaphoric zero pronoun. And state-of-the-art zero pronoun resolvers adopt a supervised approach where they train one classifier for AZP identification and then another classifier for AZP resolution. Our focus in this work is AZP resolution, which is the second step. We aim to design a model that assumes as input the AZPs in a document and then resolves each of them. AZP resolution alone is by no means easy. State-of-the-art supervised resolvers have achieved an F-score of approximately 47% for resolving manually identified Chinese anaphoric zero pronouns. But for the sake of completeness, we'll evaluate our resolution model on both manually identified and automatically identified anaphoric zero pronouns. Okay. So our contribution to this work is the proposal of an unsupervised model for anaphoric zero pronoun resolution that rivals its supervised counterparts in performance when evaluated on the Chinese portion of the on-the-nose version 5 corpus. Its main advantage is that it does not require training data manually with manually resolved AZPs. And this, together with the fact that the underlying generative process is not language dependent, means that it can be applied to languages without such annotated data. And at the core of this model is this hypothesis, and this is also the key idea behind our work, which I hopefully, you hopefully remember at least for the duration of the rest of the talk. We can apply a probabilistic pronoun resolution model trained on overt pronouns in an unsupervised manner to resolve anaphoric zero pronouns, and we'll see how this can possibly be done. Okay? So here's the plan for the rest of the talk. We'll first give a brief intro to Chinese overt pronouns because we need to rely on these overt pronouns. And then we'll talk about our generative model for overt pronoun resolution, including how we train and apply it to resolve zero pronouns. And finally, we'll show some evaluation results. Okay? Let's start with the Chinese overt pronouns. We employed 10 overt pronouns, and they are shown in the first column of this table. Each of these overt pronouns can be uniquely identified using 4 grammatical attributes, and these 4 attributes are shown in the remaining columns of the table, including number, gender, person, and animacy. So for instance, the pronoun I is singular, neuter, first person, and animate. Okay? So now let's take a look at our generative model for overt pronoun resolution. Again, this is a model for unsupervised overt pronoun resolution, not zero pronoun resolution. So this model estimates this probability of P, C, K, and L. So what are these things? P is the overt pronoun to be resolved. C is a candidate antecedent of pronoun P. K is the context surrounding pronoun P and all of its candidate antecedents. And so you can think of it as the global context in which the pronoun and the candidate antecedents appears. And finally, L is a binary variable indicating whether C is pronoun P's correct antecedent. And note that this is an unsupervised procedure. This probability is being estimated from an unannotated corpus. So in this case, we treat P, C, K as observed data and L as hidden data because this is the corpus without any coreference chains. And we'll use EM to estimate the model parameters. Okay, so let's take a look at how EM can be applied in this case. So in the E step, we use the current parameter estimates and label each overt pronoun P with the probability it co-refers with each candidate antecedent C given context K. In other words, we want to estimate this probability of L equals 1, meaning that pronoun P and candidate C are coreferent, given P, C, and K. If you have no idea of what I'm talking about, let's take a look at this example. So initially, we have these pronoun candidate pairs in our corpus, but we don't know what's the probability that the pronoun and the candidate antecedent are coreferent. And after the E step, we will be able to fill in these missing values for each pair of pronouns and candidate antecedents. So that's what the E step aims to do. Now, in the M step, we want to re-estimate the model parameters from data containing the overt pronouns probabilistically labeled in the E step, and we'll talk about what these model parameters are in just a minute. Okay, so let's take a look at the E step and the M step in more detail. Again, the goal of the E step is to estimate this probability that pronoun P and candidate antecedent C are coreferent given pronoun P, candidate antecedent C, and their context. So using the definition of conditional probability, we can rewrite this probability as the fraction on the right-hand side of this expression. Now we can rewrite the denominator P of P, C, and K as this sum because these two cases are mutually exclusive. Okay? Now, assuming that exactly one of the pronoun P's candidate antecedents is its correct antecedent, we can rewrite this probability as this. Why is that the case? Well, if you think about this, this probability refers to the case where the pronoun P and the candidate antecedent C are not coreferent, because in this case, L is 0. And because of our assumption, one of the remaining candidate antecedents of P must be its correct antecedent. And so this sum just enumerates all possible cases over all possible candidate antecedents. Okay? And this last line is just a shorthand by using the summation notation. We are summing over all the possible candidate antecedents. And so now, given these assumptions, we can rewrite the denominator as this. And if you look at these two terms, you can see that they have the same form. So let's try to simplify this joint probability. So using chain rule, we can decompose this joint probability into 4 small probabilities. And now you can see how the generative model works. It first generates the context K, and then it generates the candidate antecedent C given context K. And after that, it generates the coreference label L given candidate antecedent C and context K. And finally, it generates the pronoun P given the coreference label L, candidate antecedent C, and context K. Okay? So now again, we can rewrite this joint probability as these 4 smaller probabilities. And so let's take a look at each of these 4 probabilities in more detail. So the first one is the probability of generating pronoun P given context K and candidate C, and that pronoun P and candidate C are coreferent. So first of all, we rewrite this probability by dropping context K. And the reason is that given L equals 1, meaning that the pronoun P and candidate antecedent C are coreferent, we assume that we can generate the pronoun from the candidate antecedent without looking at the context. And if you don't know what I'm talking about, let's take a look at this example. Here, you can easily see that the pronoun he can be generated from candidate the man if they are coreferent. Similarly, the pronoun they can be generated from the women if they are coreferent. Okay? So now we rewrite this probability by representing the pronoun using its 4 grammatical attributes that we talked about earlier, including number, gender, person, and animacy. Now we can decompose this joint probability into 4 smaller probabilities. And here we are assuming that the pronouns value with respect to attribute A, such as gender, can be generated independently of other attribute values like number and intimacy, given the candidate's value with respect to A. Okay? So now we can rewrite the first probability as a product of 4 smaller probabilities. Now let's take a look at how we can rewrite the second probability, which is the probability that pronoun P and candidate C are coreferent given context K and candidate C. So first of all, we rewrite the probability as follows. You can see that we are replacing K with KC. So what exactly are K and KC? Well, K can be thought of as the global context surrounding P and all of its candidate antecedents, whereas KC can be thought of as the local context surrounding P and candidate antecedent C. Okay? So in this case, we are effectively assuming that given the local context surrounding P and C, whether P and C are coreferent is not going to be affected by the remaining context, and that's why we can drop the global context and retain or replace it with the local context. We further rewrite this probability by dropping C, the candidate, because we assume that the local context KC in this case is sufficient for determining whether pronoun P and candidate antecedent C are coreferent. Okay? So now we can rewrite this probability as this. Now let's take a look at the third probability, which is the probability of candidate C given K. Here we make this assumption, which essentially says that given context K, all the candidate antecedents of this pronoun P can be generated with equal probability. So given all these assumptions that we have made so far, let's go back to our previous slide where we said that the denominator and numerator have the same form. What we have been trying to do is to try to decompose this joint probability, and using all the assumptions we have talked about so far, we can rewrite this fraction as this. And hopefully at this point, you can see what the model parameters are. There are 2 sets of model parameters. This is the first set of model parameters. Given pronoun P and candidate C are coreferent, the probability of generating P's attribute values from candidate C's attribute values. And here is the second set of model parameters. Given the local context surrounding P and the candidate antecedent, the probability that the pronoun P and the candidate antecedent are coreferent. And so what the M step is going to do is to estimate these model parameters given the probabilities that we estimated in the E step. And if you remember, this first set of parameters actually is composed of 4 groups of parameters, 1 for each of the 4 grammatical attributes, including person, gender, number, and intimacy. Okay? And to estimate these model parameters, we simply use maximum likelihood estimation. Okay? So what have we done so far? We have described how EM can be used to learn the parameters of our model for overt pronoun resolution in an unsupervised manner. And so the question then is, how can we apply this overt pronoun resolution model to resolve our anaphoric 0 pronouns? Here's how we apply this model to resolve AZPs. So given an anaphoric 0 pronoun Z, we exhaustively search for the candidate antecedent C and overt pronoun P that jointly maximize this particular probability. The probability that overt pronoun P and candidate antecedent C are coreferent given the pronoun, the antecedent, and the context K, when this overt pronoun is being used to fill the gap left behind by the 0 pronoun Z. And the reason is that since this model is trained on overt pronouns, but it's applied to 0 pronouns, we will have to fill each of the 0 pronouns gaps with every overt pronoun when applying this model. Okay? So what remains to be done? Recall that we have these 2 sets of model parameters, and this set of parameters can be further decomposed into 4 groups of parameters. And if you look at these probabilities carefully, to compute these probabilities, we need to compute the person, gender, number, and intimacy of a noun phrase. And this is easily done, in English, but for Chinese, we don't have, a lot of resources, and so we compute these attribute values, including person, gender, number, and intimacy of an NP, either heuristically or via unsupervised learning, and the details are in the paper. For this group of parameter, which is the probability that P and C are coreferent given the context KC. If you want to compute this probability, we need to specify context. So the question is, how can we represent the context? We use 8 different features to represent context. They are all motivated by previous work on Chinese and anaphoric zero pronoun resolution. We have one distance feature, one positional feature, 4 syntactic features that are computed based on syntactic parse trees, 1 grammatical feature, and 1 semantic feature, but I'm not going to go into the details of these features here. So let's move on to evaluation, where our goal is to evaluate our unsupervised model. For evaluation, our corpus is the Chinese portion of the Ontonos version 5 corpus. For the unsupervised training of the overt pronoun resolution model, we use the Chinese training set used in the CoNL 2012 shared task, which is comprised of nearly 1,400 documents with almost 14,000 overt pronouns. And for testing, in other words, applying our resolution model to resolve anaphoric zero pronouns, we use the Chinese development set used in the CoNL 2012 shared task, which is comprised of 172 documents with nearly 2,000 anaphoric zero pronouns. And we follow previous work on Chinese anaphoric zero pronoun resolution and use recall precision F measure on resolving anaphoric zero pronouns as our evaluation measures. We evaluate our model on 3 different settings. In setting 1, we use Go parse trees and Go anaphoric zero pronouns. In the second setting, we use Go parse trees and automatically extracted anaphoric zero pronouns. And in the third setting, we use automatically extracted parse trees and anaphoric zero pronouns. And in order not to overwhelm you with a lot of numbers, I'll just show you the results obtained using settings 1 and 3 here. We have 7 baseline systems. 4 of them are simple heuristic baselines that are used to gauge the difficulty of this resolution task. And we also have 3 state-of-the-art supervised Chinese anaphoric zero pronoun resolvers. So let's take a look at the results that are expressed in terms of recall precision F measure under setting 1 and setting 3. Here we have the results of the first heuristic baseline system, which always selects the closest candidate to be the antecedent of the zero pronoun. Here is the results of the second baseline, which always selects the closest subject as the antecedent. And you can see that baseline 2 performs significantly better than baseline 1, suggesting that salience actually plays a greater role than recency in Chinese anaphoric zero pronoun resolution. Now let's take a look at the results of our third baseline, which always selects the closest semantically compatible candidate antecedent as the antecedent. And the fourth heuristic baseline, which always selects the closest semantically compatible subject as the antecedent. And you can see that these last 2 heuristic baselines are created simply by adding semantic compatibility to the first 2 heuristic baselines. And if you compare the last 2 baselines with the first 2 baselines, you can see that the last 2 outperform the first 2, meaning that semantic compatibility is indeed useful for Chinese anaphoric zero pronoun resolution. And you can see that the best heuristic baseline is the last one, and it uses both salience and semantic compatibility. Now let's take a look at our first learning-based system, which is the Zhao and Ng system. This work proposed the first learning-based approach to Chinese anaphoric zero pronoun resolution. And as you can see, unfortunately, it performs worse than the best heuristic baseline. Now let's take a look at the results of our second learning-based system, which is the Kong and Zhou system. This system resolves anaphoric zero pronouns using parse trees as structured features. It does perform better than the Zhao and Ng system, but it still underperforms the best heuristic baseline. And our third supervised baseline is our own supervised system that appeared in last year's EMNLP. It improved Zhao and Ng system with 2 extensions, and you can see that it's the best of the 7 baselines. Now, finally, the results of our unsupervised model. You can see that it performs as well as the best baseline, which again is the supervised resolver that we had from last year, although it has a high recall and a lower precision with respect to setting 3. We also did some ablation experiments to see which factors contributed most to system performance. And in each ablation experiment, we remove exactly one probability term from our model and then retrain the model. And here are the results of the ablation experiments. And here you can see that there's no drop in performance when number is being ablated, but performance drops significantly when other probability terms are ablated. In particular, you can see that the context features contributed the most to overall performance, because you can see that without the context features shown in the last row of the table, performance dropped significantly. Okay. We also take a look at the major sources of error made by our model. There are 3 major sources of error. Failure in tracking the discourse entity in focus. There are also errors in computing the semantic compatibility. And finally, the underlying assumption that overt pronouns and zero pronouns occur in the same context, which is the assumption that we rely on in our model, is not always correct. So let's take a look at the sentence. Pro are welcome. So in Chinese, this sentence is never used with an overt pronoun. And so the overt pronoun resolver that we learn from the annotated data will never acquire the knowledge that is needed to resolve this zero pronoun correctly. And in fact, this is one of the cases that can be easily handled by the supervised resolvers, but not by our unsupervised model. Okay? So in summary, we have proposed an unsupervised model for an euphoric zero pronoun resolution that rivaled its supervised counterparts in performance when it's being evaluated on the Chinese portion of the autonomous corpus. Thank you very much.
So we have time for some questions.
Well, thanks for a great talk as usual. I was just wondering about this last point that you were making, because, yeah, so at the face of it, in most languages where they have zero pronouns, zeros and overt pronouns are in complementary distribution, right? So you can hardly ever use, so it's miraculous. What you're getting is absolutely miraculous, I think. It's really a testimony to your ability and skill, but I'm really wondering how far you can push this. So
I think that this is as far as I can possibly push, but that's just my conjecture at this point. Of course, it might be a good idea to try to evaluate this model in other languages to see whether what the results we achieve here can be obtained in other languages as well. I'm not sure whether this is a result that is specific to Chinese, or whether there are other factors that made our unsupervised model achieve almost the same level of performance as a supervised model. But what I believe is that if you want to improve further, you will have to make use of annotated data. But it is possible that if we can, there's something that we can learn in an unsupervised manner, we may be able to have a semi-supervised setting where we can use a small amount of annotated data, trained resolver on the small amount of label data, and try to combine it with the output of the unsupervised model. So that is one possibility. But again, if you ask me whether we can still improve in an unsupervised manner, I don't think that it is that easy to do that.
Thanks, nice talk. Just a quick question. I suppose this work is, assume you have the golden zero pronoun. So have you aware of any work to identify the zero pronoun?
Oh, okay. So, okay, if you look at this table, we have 2 columns. One uses Go parsers and Go AZPs, and the other uses system parsers and system AZPs. What that means is that in this rightmost column, we actually generating results using automatically identified anaphoric zero pronouns.
Okay, yeah.
Thank you very much.